Today we're going to deal with one of the more important concepts in linear algebra, least squares analysis, or curve fitting. We are going to develop a model, then we will take measurements, and we will use our measurements to evaluate the parameters in our model. Now, of course, before we do that, we need to have a procedure that would minimize the error due to our choice of parameters. That's called least squares analysis. So we want to minimize the square of the errors. The four fundamental subspaces of a matrix A are the null space of A, the null space of A transpose, the column space of A, and the column space of A transpose. So these are the four fundamental subspaces of matrix A. So you've got the null space of both A and A transpose. You've got the column space of both A and A transpose. Find the basis for the four fundamental subspaces of 0, negative 1, 1, 1, 2, 0, 1, 1, 1. Well, first, we'll get the basis for the null space of A. So remember, the null space of A, we want vectors x such that A times x is equal to 0. So we have 0, 1, 1, negative 1, 2, 1, 1, 0, 1 times the vector, column vector x, y, z will equal to the 0 vector. So this would be the null space. The set of all vectors x that make this true would be the null space of A. I get a negative y plus z is equal to 0, multiply crossing down. This would give me x plus 2y is equal to 0, then x plus y plus z is equal to 0. Well, from here I can see that y is equal to z. Here I can see that x is a negative 2y. Well, let's let z be 1. If z is 1, then y is 1. If y is 1, x is negative 2. Let's make sure the last equation works. A negative 2 plus 1 is 0, so it does check. So a basis for the null space of A is going to be the set consisting of the vector negative 2, 1, 1. Now we'll get a basis for the transpose of A. So I'm looking for vectors x such that A transpose times the vector x is equal to 0. We'll look back at A. We can see that A transpose is going to be the rows and columns interchanged, so it'll be 0, negative 1, 1 will be the first column. 1, 2, 0 will be the second column. 1, 1, 1 will be the third column. So then we want to have 0, negative 1, 1, 1, 2, 0, 1, 1, 1 times the x vector, x, y, z, is equal to the 0 vector. Okay, multiplying, I get y plus z is equal to 0. The opposite of x plus 2y plus z is equal to 0. X plus z is equal to 0. Now, of course, this tells me that y is the opposite of z. This tells me x is the opposite of z. So if I let z equal to 1, then I'd have a solution as being negative 1, negative 1, 1. Because if z is 1 and x is the opposite of z, x would be negative 1. Y is the opposite of z, y would be negative 1. Well, let's check and see if this middle one works. The opposite of negative 1 is 1, so that would be 1 minus 2 plus 1 equals 0, so we see that it works. So a basis for the null space of the transpose of A is going to be the set consisting of the vector negative 1, negative 1, 1. Now to get the column space of A, I want to, and the column space of A transpose, I need to row reduce. Well, to row reduce, the first thing I'm going to do is just interchange the third row in the first row. Now, in order to get a 0 here, I'm going to multiply row 1 by negative 1 and add to 2. So multiply row 1 by negative 1, add to row 2. So negative 1 times 1 is negative 1 plus 1 is 0. A negative 1 times 1 is negative 1 plus 2 is 1. A negative 1 times negative 1 is negative 1 plus 0 is negative 1. Now I'm going to multiply row 2 by negative 1, add to row 1. And then after I do that, I'm just going to add row 2 to row 3. So I'll leave row 2 the same. I'm going to multiply row 2 by negative 1 and add to row 1. Negative 1 times 0 is 0. 0 plus 1 is 1. Negative 1 times 1 is negative 1. Plus 1 is 0. A negative 1 times negative 1 is 1. 1 plus 1 is 2. Now I'm just going to add row 2 to row 3. 0 plus 0 is 0. 1 plus a negative 1 is 0. A negative 1 plus 1 is 0. So we have it row reduced. Now remember, one way of getting the column space is to notice the rows that start with a 1 and then go back to the original matrix and pick those columns. So the column space of A is going to be our basis for the column space of A. Let's go back to the original one. The first and the second rows start with 1, so I'll take the first and the second columns. So it'll be 0, 1, 1. Negative 1, 2, 1. Now we know that the R, the column space of A transpose, is going to equal to the row space of A. Well, the row space of A is going to be 1, 0, 2, 0, 1, negative 1. You just take your non-zero rows, but I'm going to put them in column form. So it would be 1, 0, 2, 0, 1, negative 1. Now I have some important properties for you. If A is an M by N matrix, then the column space of A and the null space of A transpose are orthogonal subspaces of M space. And notice M is the number of rows. The column space of A transpose and the null space of A are orthogonal subspaces of N space. M space is the direct sum of the column space of A and the null space of A transpose. N space is the direct sum of the column space of A transpose and the null space of A. Now we're going to be using property 1 in just a few minutes, so I think I'll give you the proof of that one. So let's let B be a vector in the column space of A, and let U be a vector in the null space of A transpose. And notice that the row space of A equals the column space of A transpose. So the row space of A will equal the column space of A transpose. That's going to be important to the next step. Therefore, now if U is an element of the null space of A transpose, then A transpose times U would equal to 0. That's the definition of being in the null space. A set of all vectors such that AX is equal to 0. Well, U is one of your X vectors, and in this case we're talking about the null space of A transpose, so it would be A transpose. Now V is in the row space of A, but the row space of A equals the column space of A transpose. So V is going to be here. So then we have V dot U is 0. Well, if V dot U is 0, then that means that the column space of A and the null space of A transpose are orthogonal. That's the definition of orthogonal. Now, we are ready to solve the least squares problem. Find the straight line that best fits the data points -1, 1, 1, 0, and 3, -2. So we want to find the straight line that best fits these 3 points. Well, remember the equation of any straight line is y is equal to mx plus b. So mx plus b equals to y is the equation of any straight line. So I go to my first equation, mx plus b is equal to y. So x is -1, y is 1. Or I can put it in this form, b minus m is equal to 1. Now let's use the point 1, 0. X is 1. So I put 1 in the place of x, I put 0 in the place of y, or I get b plus m is equal to 0. And finally we use x is 3, y is -2. So in the x position I put 3, in the y position I put -2. Or if I put it in the correct order, I have b plus 3m is equal to -2. So I have a system of 3 equations with 2 variables. I can write this in matrix form as 1, -1, the coefficients matrix A, 1, -1, 1, 1, 1, 3, times the x vector, or the variable vector, is equal to the constants, 1, 0, -2. So this is writing it in the form AX equals to B. Coefficient matrix, the variable matrix, the constants. The least squares problem involves finding x that minimizes the norm of the error. Now, if we're trying to solve ax equal b, then the error is going to be ax minus b. So, what we want to do is to minimize the length of the error, or the norm of the error. So let's let S be the column space of A. So that means S is going to be, let me write that in. If S is the column space of A, that means S is RA. I'm going to use that later. B is not in S. So kind of let me show you what we're trying to do here. Here's the column space of S. Here's the vector B. So we say B is not in S. Well, the way I know that B is not in S is that if B were in S, then AX minus B equals 0 would have a solution. But AX minus B equals 0 has no exact solution. If it had an exact solution, then we wouldn't be trying to minimize the squares. We'd have the exact answer. So if we look at S, and this is B, then this would be, if we call this AX here, then this perpendicular line is the AX minus B. See, AX plus AX minus B would equal to B. So this is the AX minus B. So we need a vector AX in S that is as close as possible to B. So we need a vector AX that lies in S that is as close as possible to B. Well, that vector is the orthogonal projection of B onto S, which is denoted as the projection of B onto S. So this AX is the orthogonal projection of B onto S. That's the closest we can get. Now the rest of it is just following a string of implications. So we see that AX is the projection of B onto S. Well, this implies that AX minus B is equal to the projection of B onto S minus B. Just subtracted B from both sides. Okay, this implies that AX minus B is orthogonal to S. So AX minus B is the orthogonal projection of B onto S. So this is a right angle. So that means that AX minus B is orthogonal to S. Now, if AX minus B is orthogonal to S, then that means AX minus B is orthogonal to the column space of A, because the column space of A is S. Now, if AX minus B is orthogonal to the column space of S, then that means AX minus B is an element of the orthogonal complement of A. So if AX minus B is orthogonal to S, which is the column space of A, then AX minus B is an element of the orthogonal complement of A. But property 1 that we discussed in the proof tells us that the orthogonal complement of A is the null space of A transpose. So AX minus B is in the null space of A transpose. So if AX minus B is in the null space of A transpose, then A transpose times AX minus B is 0. That's what it takes to be in the null space. Well, doing a little algebra here, I get A transpose times AX is equal to A transpose B. I just used the distributive property, then added to both sides. To solve the least squares problem, one solves the systems of equations. AT-AX is equal to ATB for X. Well, what I would need to do is to multiply both sides by ATA inverse. If I multiply by ATA inverse on this side, it leaves me with X. Multiply on the other side, of course, I would still have it. Now, this system is called the normal equations for the least squares problem. Now let's go back and finish our problem. now that we have the formula. So with our problem, we had A, X is equal to B. So here's the coefficient matrix A, here's X, here's your constants B. Well, rather than doing all the work by hand, I went to derive, and I authored the A matrix. One, 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 negative 1, 1, 3. I authored the B matrix, 1, 0, negative 2. So the formula is X is equal to A transpose A inverse A transpose B. So A transpose A inverse A transpose B. A is 1. B is expression 2. So I put A transpose times A inverse. So this would be, I just to author this, I said author expression, I put parentheses, number 1 transpose times number 1, close parentheses, inverse, times number 1 transpose times number 2. Again, we have A transpose times A inverse times A transpose times B. I tell derive to simplify using the basic simplification, and I get that B is 5/12. M is a negative 3/4. Because my form I was using is y is equal to B plus mx. Or if we go back to our basic matrix, we had the B and the M, so the first value I get would be the B, the second value I get would be the M. So the least squares equation, or the predicted y, would equal to a negative 3/4 plus 5/12 x. So there is the equation of the line of best fit. Now I use derive to plot the lines and the point, to plot the line and the points, so you can see how close the fit actually is. Here are the 3 points. Here's the equation of the 3 points. I just had derive plot the points, then I had derive plot the line. And you can see how close it is. Pretty good fit. The least squares technique is much more general than simply fitting points to a straight line. We can fit any model. Find the least squares quadratic polynomial for the data points. With a quadratic polynomial, it's going to be the form y is equal to a plus bx plus cx squared. Or I could write it as a plus bx plus cx squared is equal to y. So let's look at each of the points. In this case, x is 0, y is 0. So I have a plus b times 0 plus c times 0 squared is equal to 0. Or I have that A is equal to 0 when I simplify. Here I have x is 2, y is 2. So I have A plus, if x is 2, that would be 2b. If x is 2, that would be 4c. 4c is equal to y is 2. So I'll just write it over here. A plus 2b plus 4c is equal to 2. With 3 and 6, I have A plus, x is 3, so that would be 3 times b, that would be 3b, plus then if x is 3, x squared is 9, that would be 9c is equal to y, which is 6. And finally, if x is 4, y is 12. So that would be A plus 4b, x is 4, 4 times b would be 4b. That's cx squared, x is 4, 4 squared is 16, so that would be 16c is equal to y, which is 12. So I have A plus 4b plus 16c is equal to 12. Now we need to write in the matrix form, AX is equal to B. Well, A is your coefficient matrix. So here we have 1, 0, 0. Here I have 1, 2, 4, 1, 3, 9, 1, 4, 16. And my variables will be A, B, C. And the constants will be 2, 6, 12. So here is the A matrix. Here is the B matrix. So I enter them into derive, and I use my formula, A transpose dot A inverse times A transpose B. So I go and enter the matrix A, 1, 0, 0, 1, 2, 4, 1, 3, 9, 1, 4, 16. This is matrix A. I enter the constants. That was matrix B. Then I author 1 transpose times 1 inverse times 1 transpose times B, or A transpose times A inverse, be sure to put the parentheses now, times A transpose times B. And I get my answers. So since I've had my vector A, B, C, then this is going to be A, B, C. So I get A is 0, which we already knew really. B is -1. C is 1. So my equation is going to be y is equal to 0 minus 1x plus 1x squared. Now again, I had derive, plot the points. So I put in my points, 0, 0, 2, 2, 3, 6, 4, 12. And I had derive, plot the points. Then I had derive, plot the equation. Here are your points. Here's your equation. You see there's a perfect fit. Now this might look like a point, but this is just a little marker on derive. You look across, and I normally make sure I have it at 0, 0 before I start, and I got a little careless. And I'd already printed it, didn't want to waste the paper. But, so this is not one of the points. If you go back and look, these are your 4 points. There is your quadratic function that fits them perfectly, or your parabola.